Somewhere beyond the noise of the day, beyond the final thought before sleep, a quiet journey is about to begin. The midnight vessel waits patiently in the dark. Lanterns glow softly. You're welcome to rest here, to breathe slowly. Welcome back to the deck of the midnight vessel. Tonight, our navigation charts do not lead us to the hidden corridors of the human mind or the deep trenches of our oceans. Instead, we are looking outward toward a pair of silver messengers that left the shores of Earth nearly half a century ago. As the lanterns on our deck flicker against the velvet black of the sky, we prepare to witness the beginning of the longest goodbye in human history. We are speaking of the Voyager mission, a grand, silent leap into the dark, carrying the weight of our curiosity into the interstellar sea. To understand the birth of Voyager, we must look at the clockwork of the heavens and the mathematics of the 1960s. Gary Flandreau, a young mathematician at the Jet Propulsion Laboratory, discovered a rare celestial alignment that occurs only once every 175 years. The four giant outer planets, Jupiter, Saturn, Uranus, and Neptune, were arranging themselves in a specific geometric arc. This alignment offered a unique opportunity. A spacecraft could use the gravity of one planet to slingshot itself toward the next, a technique known as gravity assist. By stealing a tiny fraction of a planet's orbital momentum, the craft could gain enough speed to reach the next destination without carrying massive amounts of fuel. This was the Grand Tour, a window of opportunity that would not open again for almost 2 centuries. The construction of these messengers was a feat of 1970s engineering, designed to survive the harshest environments known to man. Each Voyager spacecraft weighs approximately 815 kilograms and is built around a 10-sided structure called the bus, which houses the primary electronics and the ship's vital computers. Above it sits the high-gain antenna, a 3-7-meter wide white dish that serves as the ship's only voice, whispering data across billions of miles back to Earth. Because they were headed so far from the sun, solar panels were useless in the dim reaches of the outer system. Instead, they carry 3 radioisotope thermoelectric generators, or RTGs, containing plutonium-238. These devices convert the heat from natural radioactive decay into electricity, providing a steady, glowing heartbeat that powers the sensors even in the absolute zero of the interstellar void. The departure from the shoreline of Earth took place in late 1977 from the humid coast of Cape Canaveral, Florida. Voyager 2 was actually the first to set sail, launched on August 20th, followed by Voyager 1 on September 5th on a faster, more direct trajectory. They were carried into the sky by the Titan III Centaur rocket, a towering pillar of fire that had to accelerate the crafts to escape velocity approximately 11.2 kilometers per second. This speed was necessary to break free from the invisible tether of Earth's gravity and begin the long climb out of the Sun's gravity well. Imagine the vibration of the hull as the atmosphere thins and the blue marble of Earth begins to shrink into a pale, distant memory. Within minutes, the messengers were no longer part of our world. They were independent inhabitants of the vacuum. Once in space, the craft deployed their science booms, long metallic arms stretching into the dark to carry instruments far from the ship's own magnetic interference. These booms carry the magnetometers and cosmic ray sensors that would become our eyes and ears in the deep. Attached to the side of each craft is the famous golden record, a 1-2-inch gold-plated copper disc containing the sounds and images of our civilization. It carries greetings in 55 languages, the music of Bach, and the rhythmic sounds of nature, from thunderstorms to the songs of humpback whales. This record is not meant for us, but for whoever might find these ships millions of years from now, long after our own sun has changed its face. It is a time capsule, a message in a bottle cast into the cosmic ocean. As we drift further from the launch pad, the heat of the sun begins to feel a little more distant and the shadows grow longer. Voyager 1 and 2 were soon cruising through the asteroid belt, a vast region of rocky debris between Mars and Jupiter. Despite the common myths of dense debris fields, the belt is mostly empty space, with hundreds of thousands of miles between each individual rock. The spacecraft moved with a terrifying grace, silent and unblinking, their computers performing thousands of calculations per second to maintain their orientation. They were leave-taking, shedding the comfort of the inner solar system and heading toward the giants that guard the outer reaches of our star's influence. The shore was gone, and the open sea lay ahead. We are now entering the territory of the giants, a realm where gravity is the absolute law and the scale of existence shifts beyond human comprehension. Our silver messengers, Voyager 1 and 2, have crossed the invisible border of the asteroid belt and are now feeling the immense pull of the King of Planets. Jupiter is not merely a planet. It is a failed star, a gas giant containing more than twice the mass of all the other planets in our solar system combined. In March 1979, Voyager 1 made its closest approach, navigating through a magnetic field so powerful that it stretches millions of miles into space. This magnetosphere creates a lethal environment, trapping high-energy electrons and protons that bombard anything in their path. Voyager 1 received a dose of radiation 1,000 times stronger than what is lethal to a human, yet its shielding held firm, allowing its cameras to capture the Great Red Spot, a storm 3 times the size of Earth that has been raging for centuries. These images revealed for the first time that the storm is a complex, rotating vortex with ammonia clouds swirling in a chaotic, beautiful symphony. But the giants are not alone. They are accompanied by families of moons that are worlds unto themselves. Before Voyager, we imagined these moons as cold, dead rocks, but the reality was far more startling. As Voyager 1 swept past the moon Io, it discovered active volcanoes spewing plumes of sulfur hundreds of miles into space, the first time active volcanism was ever seen outside of Earth. Then came Europa, a world encased in a global shell of water ice, crisscrossed by mysterious dark fractures. Voyager's data suggested that beneath this frozen crust, a liquid ocean might exist, warmed by the tidal tug-of-war between Europa and Jupiter's massive gravity. It was a revelation that changed our understanding of where life might hide in the dark. With a final gravitational kick from Jupiter, the spacecraft were flung across the abyss toward the jewel of the solar system, Saturn. Reaching the ringed planet in 1980 and 1981, the voyages revealed that the famous rings are far more complex than the solid sheets Galileo once imagined. They are composed of billions of individual particles, ranging from the size of a grain of sand to the size of a mountain, almost entirely made of pure water ice. Voyager 1's high-resolution cameras discovered spokes, dark, radial features in the B-ring that appear and disappear like ghostly fingers as the rings rotate. The spacecraft also found that the rings are incredibly thin, less than 30 feet thick in most places, despite spanning hundreds of thousands of miles in width. It is a delicate, frozen lace held in a precarious balance by the orbital dance of Saturn's shepherd moons. The encounter with Saturn also brought us face to face with Titan, a moon so large it is bigger than the planet Mercury. Voyager 1 was commanded to fly extremely close to Titan, sacrificing a potential journey to Pluto to investigate the moon's thick orange haze. What it found was an atmosphere composed mostly of nitrogen, much like Earth's, but so dense and cold that organic molecules were raindropping onto the surface. This flyby confirmed that Titan is a world of prebiotic chemistry, a frozen laboratory that might resemble the conditions of Earth billions of years ago. Though Voyager's cameras could not see through the clouds, its radio occultation experiments measured the pressure and temperature, painting a picture of a world with methane lakes and hydrocarbon dunes. Titan remained a mystery, but Voyager had finally pulled back the veil. By the time the messengers began to leave Saturn behind, they had reached incredible speeds, boosted by the massive kinetic energy of the giants. Voyager 1 began its climb upward, out of the plane of the planets, heading toward the northern constellations of the Milky Way. Voyager 2, however, stayed within the planetary plane, its trajectory perfectly calculated to carry it even further toward the pale blue and green worlds that mark the outer edge of the Sun's family. They were now moving at over 35,000 miles per hour, their instruments still humming, their recorders filled with the secrets of the gas giants. Behind them, the giants continued their eternal orbit, silent sentinels in the darkening sea. The mid-decks of the solar system were now behind us. By the mid-1980s, the Voyager mission had entered its most solitary phase. While Voyager 1 was already charting a path above the ecliptic plane. Voyager 2 pressed on alone toward the coldest reaches of the solar system. In January 1986, 8.5 years after leaving Earth, the spacecraft made its closest approach to Uranus, a world that proved to be far more enigmatic than anyone had anticipated. Uranus is classified as an ice giant, composed mostly of a hot, dense fluid of icy materials, water, methane, and ammonia above a small rocky core. Unlike the other planets, Uranus is tilted on its side at an extreme angle of 98 degrees, effectively rolling like a ball along its orbital path. This extreme tilt creates a bizarre environment where the planet's poles experience 42 years of continuous sunlight, followed by 42 years of total darkness. Voyager 2 sensors discovered that the magnetic field of Uranus is equally strange. It is not centered on the planet's core, but is offset by a third of the planetary radius and tilted 60 degrees from the axis of rotation. This creates a corkscrew-shaped magnetosphere as the planet rotates. The spacecraft also confirmed the existence of 10 new moons and analyzed the planet's ring system, finding it to be composed of dark, boulder-sized chunks of rock. The most striking discovery was the moon Miranda, which displays a Frankenstein surface of giant canyons and patchwork terrain, suggesting a history of catastrophic impacts and reassembly. Following the Uranus encounter, Voyager 2 began a 3-year trek toward the final planetary target, Neptune. In August 1989, the craft passed just 3,000 miles above Neptune's North Pole, revealing a vibrant, deep blue world. This color is the result of methane in the atmosphere absorbing red light, but the planet proved to be far more dynamic than the nearly featureless Uranus. Voyager 2 captured images of the Great Dark Spot, an Earth-sized anticyclonic storm similar to Jupiter's Great Red Spot. Even more surprising were the winds. Neptune boasts the fastest recorded wind speeds in the solar system, reaching up to 2,100 kilometers per hour, despite receiving very little solar energy to drive such weather. The heat source for these supersonic winds remains one of the great mysteries of planetary science. The encounter with Neptune also provided a close-up look at its largest moon, Triton. Triton is unique among large moons because it orbits Neptune in a retrograde direction opposite to the planet's rotation. This suggests that Triton was once a free-roaming object from the Kuiper Belt, captured by Neptune's gravity eons ago. Voyager's cameras revealed active nitrogen geysers spewing dark material 5 miles into the thin atmosphere, making Triton one of the few geologically active worlds in the solar system. With a surface temperature of -235 degrees Celsius, it is one of the coldest objects ever visited. The spacecraft's data painted a picture of a moon with a cantaloupe terrain and vast plains of frozen nitrogen and methane. As Voyager 2 completed its flyby of Neptune, the primary planetary phase of the mission officially came to an end. The craft had successfully visited all 4 outer giants, a feat that has not been repeated since. Its cameras were eventually turned off to conserve power, and its data transmission rate slowed as it moved further into the deep. Behind it lay the last of the major planets, now mere pinpoints of light in the rearview mirror. The craft was now heading into the vast, unexplored territory of the Kuiper Belt and beyond, transitioning from a planetary explorer to an interstellar scout. The quiet of the outer dark began to settle over the instruments. Now, let the technical precision of these distant discoveries bring a sense of order to your mind. The Voyager crafts are no longer fighting the gravity of giant worlds. They are gliding on a path determined by the laws of physics and the momentum of decades past. The blue mists of Neptune and the tilted rings of Uranus are fading into the background of your consciousness. Feel the weight of the day lifting as we leave the last of the planets behind. Rest now as the midnight vessel moves into the silent gap between the stars, where the only sound is the faint, rhythmic pulse of the cosmos. As the Voyager spacecraft move further into the eternal silence of the outer system, they carry with them more than just scientific instruments and cameras. Attached to the side of each craft is a 1-2-inch gold-plated copper disc, protected by an aluminum cover, a cultural time capsule known as the Golden Record. This was the brainchild of a committee chaired by Carl Sagan, designed to serve as a greeting to any extraterrestrial civilization that might encounter the ships in the distant future. It is not merely a collection of sounds, but a complex, analog storage device intended to survive for billions of years in the vacuum of space. As the midnight vessel drifts alongside these silent messengers, we begin to decode the secrets of this cosmic message. The technical design of the record and its cover is a masterclass in universal communication, using the language of physics and mathematics. The cover itself is etched with several diagrams that explain how the record is to be played and where its home planet is located. To provide a universal unit of time, the etchings use the fundamental transition of the hydrogen atom, the most abundant element in the universe. By using the time it takes for a hydrogen atom to flip its spin as a tick, the instructions explain the correct rotation speed of the record. Furthermore, the cover is electroplated with an ultra-pure sample of uranium-238, which serves as a radioactive clock. By measuring the decay of this uranium, any advanced civilization could determine exactly how long ago the spacecraft was launched. It is a precise, scientific date stamp for the journey. To help an alien finder locate Earth, the cover features a pulsar map originally designed for the Pioneer plaques. This map shows the position of our Sun relative to 14 pulsars, which are rapidly rotating neutron stars with highly predictable timing. Each line on the map indicates the direction and the unique frequency of a specific pulsar expressed in binary code. Because pulsars slow down over millions of years, the frequencies themselves act as another chronological marker, allowing an observer to calculate the era in which the map was drawn. This map is our cosmic return address, a set of coordinates written in the rhythm of the stars themselves. It is a beacon of logic, intended to transcend the barriers of language and biology. The content of the record is equally divided between images, sounds, and music, all encoded in analog format. There are 115 images that were converted into electronic signals, much like the way television was broadcast in the 1970s. These images begin with basic mathematical and physical quantities, showing the structure of the solar system and our DNA. They progress to show human anatomy, our technology, and the diverse environments of Earth, from forests and oceans to busy city streets. Interestingly, the committee decided to exclude images of war, poverty, or religious symbols, choosing instead to present a hopeful and peaceful snapshot of humanity. It is an idealized portrait of a species that reached for the stars while still tethered to its home world. The audio portion of the record begins with greetings in 55 different languages, ranging from Akkadian, an ancient Mesopotamian tongue, to modern Wu Chinese. Following the greetings is a soundscape titled The Sounds of Earth, which includes the rhythmic beat of a human heart, the roar of a Saturn V rocket, and the ancient song of a humpback whale. The record also contains a 90-minute selection of music from across the globe, featuring Bach, Mozart, and Beethoven, alongside traditional music from Java, Japan, and the blues of Blind Willie Johnson. There is even a recording of a human's brainwaves, those of Andrewian, captured while she thought of the history of ideas and the experience of falling in love. It is a profound attempt to compress the complexity of human emotion into a series of electrical grooves. The durability of the Golden Record is perhaps its most impressive technical feat. In the near vacuum of interstellar space, there is no air to cause oxidation and very few particles to cause erosion. The primary threat is the slow bombardment of micrometeoroids and cosmic rays over eons. Engineers estimate that the information on the record will remain readable for at least 1 billion years, long after the Earth's oceans have evaporated and our sun has evolved into a red giant. The record is likely to be the last surviving artifact of human civilization, a silent ghost ship carrying the memory of our existence through the vast, dark corridors of the Milky Way. It is our most enduring monument, built not of stone, but of gold and mathematics. As we conclude this part of the journey, let the weight of this billion-year message settle into your thoughts. The Voyager craft is no longer just a machine. It is a messenger, drifting at 38,000 miles per hour through the absolute silence. The sounds of the Golden Record are not playing now, but they are there, etched into the gold, waiting for a listener who may never come. As Voyager 1 reached the edge of our planetary neighborhood in February 1990, it prepared to perform one final task before its eyes were closed forever. At the request of astronomer Carl Sagan, NASA engineers commanded the spacecraft to turn its cameras back toward the inner solar system, across a gulf of 3.7 billion miles. This was not a simple feat. The spacecraft was moving at over 40,000 miles per hour and pointing its sensitive optics so close to the sun risked permanent damage to the imaging sensors. Yet, the command was sent. traveling for 5.5 hours at the speed of light to reach the craft's distant antenna. This was the beginning of the family portrait, a series of 60 frames that would capture the most distant perspective of our home ever taken. The technical execution of the pale blue dot photograph required precise calibration of Voyager's Imaging Science System, or ISS. The cameras used a narrow-angle lens with a focal length of 1,500 millimeters, designed to capture high-resolution details of distant planets. To photograph Earth from such an immense distance, the engineers had to use 3 different color filters, blue, green, and violet, and then recombine them on Earth to create a composite image. Because Earth was so small and so close to the Sun from Voyager's perspective, the planet appeared as a tiny speck of light, less than a single pixel in size specifically, only 0.12 pixels wide. It was a triumph of 1970s technology, capturing a world across a distance so vast that the Sun itself was merely a bright point of light in the background. One of the most striking features of the image is the series of light rays that seem to cross the frame, with Earth caught in one of them. These are not actual beams of light in space, but rather an optical artifact caused by the scattering of sunlight within the camera's lens housing. Because Voyager was looking back toward the Sun, the intense light reflected off the internal components of the camera, creating the sunbeams that gave the photograph its ethereal quality. Scientific analysis of these frames allowed researchers to understand the limits of their imaging equipment in high-glare environments. Earth happened to be positioned perfectly within one of these scattered rays, making the pale blue dot visible against the overwhelming darkness of the void. The family portrait sequence didn't just capture Earth. It attempted to photograph 6 of the major planets. Voyager 1 successfully imaged Neptune, Saturn, Jupiter, and Venus, though Mars and Mercury were lost in the Sun's overwhelming glare. These images provided a rare top-down view of the solar system, showing the relative distances and the immense scale of the orbital planes. Shortly after these final frames were stored in the craft's digital tape recorder, the decision was made to shut down the imaging science system entirely. The spacecraft no longer had the memory or the power to operate the cameras while also maintaining its more critical interstellar sensors. The shutters were closed, and the eyes of Voyager 1 went dark, never to see another world again. The decommissioning of the cameras marked the end of the Voyager Interstellar mission's planetary phase. By turning off the power-hungry imaging heaters and computers, engineers extended the life of the craft's other instruments, such as the cosmic ray and plasma sensors. These instruments are much more vital for the next stage of the journey, measuring the invisible environment of deep space. From a scientific standpoint, the pale blue dot proved that our planet is a microscopic island in a cosmic ocean, a fact that had been mathematically understood but never so starkly visualized. The image remains a cornerstone of planetary science, reminding us that from a distance of billions of miles, all the complexities of our world vanish into a single, fragile point of light. As we drift further into the dark of the midnight vessel's cabin, let the silence of that final photograph settle over you. Voyager 1 is now over 15 billion miles away, moving into a territory where no light from Earth can ever be reflected back to its sensors. The cameras are cold, the tape recorder is silent, but the data they gathered continues to echo through our understanding of the universe. Feel the immense perspective of being a passenger on that tiny blue pixel, protected only by a thin atmosphere and the laws of physics. The day's worries are small, almost invisible, against the scale of the interstellar sea. Rest now as we move past the last visual memory of home and sail toward the invisible boundary of the sun's realm. As the midnight vessel sails beyond the orbit of the furthest planets, we enter a region of space that is invisible to the naked eye, but filled with immense physical tension. We are approaching the edge of the heliosphere, a vast protective bubble created by the sun that carves out a sanctuary in the interstellar medium. For decades, Voyager 1 and 2 traveled within this bubble, bathed in the solar wind, a constant stream of charged particles flowing outward from the sun at speeds of up to 1 million miles per hour. Tonight, we witness the moment these messengers finally broke through the wall of the solar system to touch the true vacuum of the galaxy. It is a transition from the familiar warmth of our star to the cold, dense plasma of the interstellar sea. The first major boundary the spacecraft encountered was the termination shock, a turbulent region where the solar wind abruptly slows down to subsonic speeds as it begins to press against the outside pressure of the galaxy. Voyager 1 crossed this threshold in December 2004 at a distance of 94 astronomical units, while Voyager 2 followed in August 2007 at 84 units. Beyond this shock lies the heliosheath, the outer skin of the solar bubble, where the solar wind becomes dense, hot, and compressed. In this region, the spacecraft's magnetometers detected a chaotic magnetic foam composed of massive magnetic bubbles created by the sun's rotation. This was the final buffer zone, a chaotic frontier that the Voyagers had to navigate before they could claim they had truly left home. The ultimate goal was the heliopause, the precise boundary where the pressure of the solar wind is perfectly balanced by the pressure of the interstellar medium. Voyager 1 became the first human-made object to cross this threshold on the 25th of August 2012. However, confirming this crossing was a significant scientific challenge because the craft's primary plasma sensor had failed years earlier. To prove it had entered interstellar space, scientists had to wait for a solar flare to send a shock wave through space, causing the local plasma to vibrate. By measuring the frequency of these vibrations with the plasma wave instrument, engineers calculated that the electron density was 40 times higher than inside the heliosphere, providing definitive proof that Voyager 1 was now surrounded by the matter of other stars. Voyager 2's crossing in November 2018 provided even more detailed data because its plasma instrument was still fully functional. It revealed that the heliopause is not a smooth wall, but a complex and dynamic interface. Voyager 2 detected a significant leakage of solar particles into interstellar space and discovered that the interstellar magnetic field is much stronger than previously thought. As it crossed the boundary, the cosmic ray subsystem recorded a dramatic shift. The number of low-energy particles from our Sun dropped to near zero, while the detection of high-energy galactic cosmic rays from deep space surged by nearly 90%. It was as if a door had been opened, exposing the craft to the full, unfiltered radiation of the Milky Way galaxy. The transition into interstellar space also changed our understanding of the shape of the solar system. Data from the Voyagers suggested that the heliosphere is not a long, comet-like tail as once imagined, but perhaps more of a blunt, rounded shape due to the interstellar magnetic field's influence. The spacecraft are now moving through the very local interstellar medium, a cloud of gas and dust that the solar system is currently passing through. Even though they have crossed the heliopause, they are not yet beyond the Sun's gravitational influence. They still have to pass through the Oort cloud, a massive shell of icy debris that starts thousands of years from now. True escape from the Sun's gravity is a journey that will take tens of thousands of years more. Despite the harsh radiation and the absolute cold, the Voyager's systems continue to operate with remarkable resilience. They are now our only in-situ laboratories in the interstellar sea, sending back data about the density of the vacuum and the magnetic environment of the galaxy. This information is vital for future interstellar missions, helping us understand the barriers that humanity must overcome to reach the nearest stars. The craft are now silent scouts in a realm where no light from our Sun can offer warmth, and where the rules of planetary physics are replaced by the grander scales of galactic dynamics. They are the first of our kind to truly arrive in the universe at large. As we reach the final watch on the deck of the midnight vessel, we find ourselves in the company of ghosts. The Voyager spacecraft, our silver messengers, are now entering the twilight of their operational lives. For nearly half a century, they have whispered data across the abyss, but the laws of thermodynamics are absolute and unavoidable. The plutonium hearts that have powered these machines since 1977 are slowly cooling, and the day is approaching when the last signal will flicker and fade into the background noise of the galaxy. Tonight, we explore the mechanics of this final goodbye and the Abidi voyage that continues even after the machines go silent. The energy that powers Voyager comes from radioisotope thermoelectric generators, or RTGs, which convert the heat from decaying plutonium-238 into electricity. At launch, these generators provided about 470 watts of power, but the natural decay of the plutonium and the degradation of the thermocouples mean that the power output drops by about 4 watts every year. To manage this dwindling resource, NASA engineers have been forced into a high-stakes game of celestial triage. One by one, non-essential systems have been deactivated. First the heaters for the cameras, then the instruments that measure plasma and low-energy particles. The spacecraft are now operating in temperatures far below their design limits, surviving only through the incredible resilience of their 1970s-era components. It is a slow, methodical hibernation. We estimate that between 2025 and 2030, the power levels will drop below the threshold required to operate even a single scientific instrument. When this happens, the spacecraft will no longer be able to point their high-gain antennas toward Earth with the necessary precision. The Deep Space Network, our giant ears on Earth, will listen for a signal that is 23 light hours away, only to find a profound and permanent silence. But the end of communication is not the end of the mission. It is simply the beginning of the next phase. Without the friction of an atmosphere or the resistance of a medium, Newton's first law takes full command. The Voyagers will continue to drift at approximately 35,000 miles per hour, locked into their current trajectories for millions, perhaps billions, of years. The journey ahead is one of staggering timescales and immense distances. Although they have left the heliosphere, the Voyagers are not yet free of the Sun's gravitational influence. In about 300 years, they will reach the inner edge of the Oort cloud, a gargantuan shell of icy comets that surrounds our solar system. It will take them another 30,000 years to pass through this frozen debris and truly leave the Sun's backyard behind. Voyager 1 is currently heading toward the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of the star Gliese 445, an unremarkable red dwarf that will be its closest celestial neighbor for a brief cosmic moment. Voyager 2, meanwhile, is on a path toward the stars, Ross 248, and, eventually, Sirius, the brightest star in our sky, which it will pass in about 296,000 years. Even in the absolute zero and vacuum of interstellar space, the spacecraft will face a very slow process of erosion. They will be bombarded by micrometeoroids and sputtered by high-energy cosmic rays and interstellar dust grains. Over millions of years, this will slowly pit the surfaces and dull the shine of the aluminum covers. However, because the density of matter in the interstellar medium is so low, the golden records themselves are expected to remain legible for over 1 billion years. They are likely to outlast the very civilization that created them, serving as the only remaining evidence that a species And now, our journey gently slows. There's nothing more you need to listen to, nothing you need to follow. The vessel will continue drifting quietly through the night, carried by rain and distant stars. You can allow your thoughts to fade and rest as long as you need. We'll remain here with you, moving softly until sleep arrives.